Okay, so the next presentation is Glen Mbeng from the University of Innsbruck, who's talking to us about counterdiabatic rotated ansatz for many body systems. Glen, over to you.
Okay. Yeah, thank you very much for the opportunity to talk here, Paul. And this talk is going to be about, again, about contrabatic driving. And I'm going to actually take one portion of one part of what Adolfo discussed and extend that with the contribution we did in Innsbruck. So first of all, I will start giving some generalities that have been given many times in this conference. So this is the usual quantum annealing paradigm. We start from an optimization problem and a classical optimization problem, and we map it to a quantum problem. We have a target Hamiltonian that then encodes the problem, and the goal is to find the ground set of a target Hamiltonian. And in this case, we to have quantum effects, we add a driving Hamiltonian, which usually is assumed to be the transverse field, a transverse field driving. So to solve the problem, then we use a Schrödinger dynamics, where we consider this interpolated Hamiltonian, which interpolates between the initial driving, the driving Hamiltonian, and the final target Hamiltonian. And we allow it to evolve for a total time tau. So the goal, as we said, is to have a final state at the end of this evolution, such that the final state describes or approximates the ground state, and then we can consider this to be our algorithm that solves our initial problem. And the question that I'll be tackling in this talk mainly is how can we build or choose these schedules, A of t and B of t, that are used in the interpolation. So the usual way to choose the schedule is based on the adiabatic criterion, and in this case the system is interpolated with an interpolating function which interpolates slowly between the initial and the final Hamiltonian, and the adiabatic criterion assures that essentially if we move sufficiently slowly, the system will remain in its ground state. And therefore, if we initialize in the ground state of the driving Hamiltonian, we will also be able to solve our problem. So this means essentially when one goes to check the theorems, at least for the global case, without going to local conditions, this would mean that the total time will be proportional to 1 over the gap square, the minimum gap squared. So this for hard problems with small gaps or near to phase transition means that long running times, which may be a hindrance because of coherent times, which are limited, and also because if one is seeking for a quantum advantage with this kind of algorithm, long times may just wash out this quantum advantage. And yes, so that will be the case for this. So one thing then that can be done for this kind of problems is to attack this problem is to try to optimize these schedules that we define, and there is one optimization criterion is to use this local adiabatic property, therefore to not slow down as the minimum gap, the whole schedule, but to slow down the schedule only locally. So to slow down in some fixed position depending on where the gap is closing. And this approach was also used by Roland Serf to obtain the speed up in the Grover algorithm. So I just want to mention again that for this kind of problem was the Grover problem is just the search of an item in an unsorted database, and for this kind of problem they found that without this kind of schedule optimization and taking standard linear schedules, this speed up is not achieved in general. And the other approach that I'll mainly focus on today is contrabatic driving, which Adolfo has already introduced extensively. So I just want to mention, before moving to contrabatic driving, some results, works we did in constructing this, in optimizing the schedule based on this local adiabatic criterion. So the problem with local adiabatic criterion is that usually it requires somebody to know the spectrum exactly. So what we tried to do was to try to devise an iterative construction such that that doesn't use this spectral information, which would be a problem for quantum annealing, since you would need to already have the solution of the problem before solving it. So that's a bit of a mess. So we did this, first of all, for the transverse field Ising chain. Okay, so here I show the phase diagram of the transverse field Ising chain, and it has a critical point, okay, for h equal 1, and that's where the gap is closing. So that's where the problem is hard. So we study this kind of interpolating problem where we we interpolate the target Hamiltonian and the initial Hamiltonian, and the position of the gap, of course, changes depending on the values of h. And what we find is the strategy we try to use to optimize this kind of problem is to first digitalize the schedule, okay, and start from a digital optimization. So this is for practical reasons, because it's I would say more common to use this kind of search and variational algorithms in the context of digital optimization, but also with variational annealing and schedule like this, we would imagine that some similar result can be obtained by using some parameterized continuous function. So in this case, what we do is we gradually increase the number of points used in the discretization of the schedule, and then we start a local search for the new optimal with the information we obtain from the previous iteration. If we do this in an iterative way, we find that we are able to find a schedule which actually slows down in where the gap closes. And what we find is that remarkably, when one takes into account sums the cost of finding the schedule, optimizing the schedule, and compares it with the cost of doing direct annealing, for example, a linear schedule, this approach also wins. So not only because the final performance is better, but also when one takes into account the time necessary to find this kind of schedules.
Would you like a pointer? Point to the screen.
Oh, okay. Yes, thank you very much. Okay. So we generalize this approach to other systems. For example, we tried it to optimize binary perceptron, and we also found that in general this kind of approach is useful to avoid barren plateaus in this kind of algorithm. So it also helps speeds up the optimization. And I should mention that in a more complicated problem, the story is not so simple, but the approach has to be slightly modified to take into account the fact that you can get stuck in local minima. But I will not discuss this modification in this talk. So now I'll move to the other approach, which is that we consider, which is contrabatic driving. Okay, and there are a few reviews for this approach, and essentially I will here repeat it again, mainly because it's a recorded talk, and but Adolfo already discussed at least this slide in detail. So we consider our Hamiltonian that we that parameterizes our path we want to follow, and it's a time-dependent Hamiltonian that we can diagonalize. Sorry, and we consider its spectrum. So the idea of contrabatic driving is that we want to add a term to the Hamiltonian, here A, which is meant to suppress transitions. So in the usual picture of the waiter, if the waiter doesn't move, everything is fine, the glass is not pouring. If the waiter moves slowly or starts a bit accelerating and is not an expert waiter, like someone like me, he will just pour the water. However, an expert waiter is able to move his hand in such a way that, and the plate in such a way that they generate forces that counterbalance the transitions that should happen, and in the end, the net effect is that the glass of water, the water stays in the glass. So we would want something like that. We would want the system to stay in the ground state as the water stays into the glass. So we have to add the terms, and as we said, as Adolfo already mentioned, here I don't even give the derivation in detail. So one can directly compute, so this has been done already, let's say 2002, one can directly compute what's the exact term that has to be added in such a way to have that all transitions are suppressed. So if this term is used, the final ground state is correctly the final state is exactly the ground state. However, for many body systems, we have some problems. We have that this approach heavily uses spectral information, and it adds terms to the Hamiltonian which are non-local and may give rise to problems. So, these kind of problems were tackled in the community by various authors. Here we consider the solution given by Sells and Polkovnikov based on variational local contrabatic driving. So the idea is that the problem of finding this exact driving can be written as a minimization problem, where one has to minimize this action, okay, and this action is essentially the square trace, the trace of the square of an operator. So this minimization doesn't involve diagonalizations anymore and can be performed without spectral information. Of course, how hard this is to minimize is going to be as hard as diagonalizing if one uses a whole, one wants to find the exact solution. So the idea is that instead of finding the exact solution, one can restrict the minimization to a subset of operators, which possibly should be allowed in experimental setup. Here, for example, the case of a local ansatz with just local fields, and in this case, one can the algorithm will proceed like this. One chooses the ansatz before, optimizes the action with this ansatz to get a good approximate solution for the variational parameter in the ansatz, which I should specify would turn out to be time dependent, of course. And then one evolves the Hamiltonian, then evolves the system with the corrected Hamiltonian where the new terms have been added. So, so how does this fare with what we had before? So now it's approximate, of course, but I would say that expecting to have non-approximate thing which work perfectly in many body systems is not really reasonable. And on the other hand, for the use of spectral information and adding non-local terms, we solve this problem because we can choose the ansatz appropriately, and it doesn't require spectral information. So, for the case of the one question one may have, first of all, is how do this kind of local approach, how does it scale when one performs with scaling with the system size? Is it scalable, or does it give an improvement that maybe it's only appreciable for small system? Because, for example, in the limit of one spin is exact, but if we increase the number of spins, it's gonna perform worse. So we studied this first of all in an Ising chain. So we have a disordered Ising chain where the presence of a longitudinal field makes the problem non-integrable. So it's not like there are no tricks to use from integrability theory, and we use a one local ansatz with this. This is the one nice one would like to have because it's more closer to what can be done in an experiment, and this two local ansatz, which has definitely terms which are still with two body interaction, but more complicated to implement. So we can optimize this. We use the density matrix renormalization group. So basically we use MPS and TBD to do these simulations because the system is 1D and we are trying to approximate a low energy dynamics. These techniques work pretty well. And what we see for the approaches is that compared to the standard quantum annealing, if we look at the final ground state probability at a fixed time, here the time is 1 if you want to have the parameters, sorry, and the j's are random between -1 and 1, same for the b's. So if you have that the ground state fidelity, of course, goes down as the system size increases, but the slope which goes down in this log lim plot, it changes from the quantum annealing case to the contradiabatic case with one local ansatz. So what we find is that for this case, we would say that we are getting some polynomial advantage in using this ansatz, which is actually an acceptable ansatz compared to the standard annealing case. So we repeated the same analysis for a fully connected Ising model, still with random couplings. And in this case, we found something slightly different. So what we find is that the one local driving is actually gives still an improvement. We see here goes from the red to the blue one, so the fidelity are improving. However, we find that the slopes are more or less matching, and we couldn't identify any advantage regarding this the scaling. So to get a scaling advantage, we were forced to consider a more, let's say, general form for the potential we have to add, and in this case, what we find is that the two local potential is able to find again a polynomial advantage. So from here, what would conclude is that this one local approach for systems which have higher connectivity seems to be not suitable if one wants to scale and gain some scaling advantage or some advantage which improves with the system size. And this was actually our starting point, okay? So from here, the question is, just want to mention that, of course, here we are not yet talking about just schedule optimization because we have to add other terms. So here, till what I discussed till now, we are adding other terms as usual in the Contrabatic approach. So we consider, to try to solve this problem, we consider the approach of considering contrabatic driving in rotated frames. And the idea is that we can rewrite our Schrödinger equation in a rotated frame where we have introduced this frame rotation. And now for the psi tilde, the equation, the Schrödinger equation reads this one with a new Hamiltonian HRA, which we have here. And the game is that if we have some additional boundary condition on the rotation, so that the rotation is kept to the identity, for example, at the beginning and the end, so that for the tilde variables and the standard variables, the initial and final state coincide. We have that this defines an alternative shortcut, so an alternative way to get to from the initial state, which now will coincide with our psi0, to the target state, or to the approximate target state. We use some approximate method, or we had some errors to get there. And the main thing would be that in this kind of approach, we have to play a game, right? Because we want to find the R, so the rotation, and the variational in this case, the variational potential, in such a way that this will give a simple protocol. In particular, we aim at having protocols which only have a change of schedule. So what we did was to develop a possible way to tackle this problem. So first of all, we rely again on the variational approach by Sells and Polkovnikov, and this requires us to start by identifying the potential we are adding to the Hamiltonian. So if we start from our hypothesis of the rotated frame, we get this kind of potential here. The problem is that this potential depends simultaneously on R and R dot, which are the rotation, where R is the rotation. And if we want to see R and the final Hamiltonian as our variational parameter, this is a problem, because we cannot optimize when the potential also depends on the derivative of the variables. So to solve this problem, we use a reparameterization approach, and we reparameterize in terms of auxiliary potential. This is a K, I don't know if it's possible to read it, and this is a Q. So we call them K and Q, this auxiliary potential that describe that we use for the reparameterization. And here we show how the R are written in terms of auxiliary potential. K plays it's a shift on the Hamiltonian, so the final simple Hamiltonian we want on the rotated Hamiltonian, and Q is I would say a generator for the RT for the rotation. So to proceed and have something we can compute, or I think maybe it's possible to compute also without this hypothesis, but we have to assume that the Q are commuting with each other. So this is an additional hypothesis we need to proceed. And if we do this, then essentially we finally get to this result where the Hamiltonian we have to apply to drive the system is the initial Hamiltonian plus K plus the derivative of Q. And the operator we have to optimize so the potential we have to optimize within the Polkovnikov and Sells approach is this one here. So if we plug this one into the, actually let me go step by step. It's better if we first consider select our ansatz, which should contain only the operators which are allowed in the experiment, for example. Then we plug them inside A, and then we plug A into S, and then we can minimize S with respect to the variational parameters of the operators. And finally, we run the algorithm or the protocol with the HRA that we define here. So this should provide an alternative shortcut to adiabaticity. So we tested this in the case of 2 spins. So this is a simple problem, can actually be reduced to a 2-level problem. So the exact solution is known. Yeah, and here are the details on the schedules we consider, but that's what I'll say would hold in general for any schedule. So for the rotated ansatz, we choose potential which are compatible with the initial choice. So again, here we have to choose the terms which will not generate terms which are not in the Hamiltonian, and that's what we do. We choose the terms that are in the Hamiltonian, and this leads to the rotated Hamiltonian, which has the same formal expression as the original Hamiltonian, just with different coefficients, which I would say means we are changing the schedule. If we can find this, as we said, by optimizing the action. We do this by local search and by doing an iterative search, so searching from one time, jumping to the following. And in this case, it's pretty easy because we expect these functions to be continuous. And the result is, as we show here in the picture, that the optimization gives for the schedules, the result would get by finding them exactly, because in this problem it's so simple that we know the exact results for the variational parameters. So now we go to, we plug the variational parameters we found through the optimization within the expression for the schedules, and we test how the schedule works. So we know it should work perfectly, but since we found the parameters variationally, we would not be sure. And just to say, we have a fidelity here, which the black line is the unassisted driving, where we had simple driving without any modification of the schedule. And then we have this is the new schedule that we are applying, in this case for the blue curve. So the blue curve shows the fidelity, so we have a dip because we are working in the rotated frame, and in the rotated frame would have no dip, as shown by this light blue line. But in our lab frame, we'll see that eventually the fidelity goes to unity only at the end of the schedule, and achieving a perfect state transfer for the problem. So we tested this in more complicated setups. So first of all, we consider a quadratic architecture where essentially it's all-to-all with some random couplings. And again, we have standard quantum annealing schedules for the problem. So we apply our rotated ansatz. Still, we have that we choose it to be compatible with the initial Hamiltonian, so that we do not generate extra terms. We just have a modification of the schedule, as we see here. And first of all, what I want to say is that the cost of computing the action is not high. It scales as n squared, so it's something which can be done. So we do it, and we have no problem with optimization. It scales polynomial with a small exponent, and we can compute it also for large system without a problem. But simulating the system is what's a problem then later. So here I show the schedules we get for this fully connected system, and then I mean, it's exactly the one shown in the picture, and I show a comparison between the unassisted driving, the local contrabatic driving, which adds some contrabatic terms, and our rotated ansatz, which doesn't actually add any terms, but uses this modified driving that we computed by classically before running the algorithm. And we see that the rotated approach finds fidelity which are better than the other approach. Here I'm showing data compared to the time evolution of a single, for a single annealing time equal to 1, and for a single system size, which is 8 if I count correctly. Yes, it's 8. And what we do then is we try to see the scaling, how it scales. We compute the degree of improvement, which is a fancy way to say that is the ratio between the fidelity of the unassisted driving and the new fidelity we get. So in the local driving, we find, again, as we found before, no news. There was no scaling improvement, but the RA driving actually also provides a scaling improvement when compared with the system size. So there is an improvement in the way the fidelity scales with the system size. So I will just quickly mention that we tried this also in the different setup of parity encoding. So the goal in the parity encoding is to embed the system of a highly non-local graph into a 2D architecture, and it does this by arranging this, by encoding the links of the relative parity of the spins into one variable, as we see here. And once this is done, we have to add some constraint to the system, because when we go through a loop of such links, we get back to the final spin, and we have to have that this is aligned with itself. So essentially the product of these elements must be 1. And this constraint can be imposed by adding 4 body constraints to the Hamiltonian, and once this is done, we get a mapping which maps actually such that the final Hamiltonian low energy configuration corresponds with the initial ones, as long as it's sufficiently large. And we also get that the whole problem encoding is encoded in local fields. So we did the same thing. I'll not maybe just repeat all of the details again, because the procedure is exactly as the one I discussed for the previous system. And what here is this slightly different, that we have an extra control term for the Hamiltonian, because we allow the control term for the constraints of the Hamiltonian to be free and to be as a free controlled parameter. And this is not a problem. We can handle this as well, and we do the optimization again. We do the approach. We have again that the form is the usual one, so we have just a schedule modification, and here we show the schedule modification suggested by our approach. And the fidelity shows that indeed there is an improvement. Here I show the dynamics for this particular system that we consider still as fixed time, and the rotated ansatz approach by schedule modification is able to improve the fidelity of the system. And again, we find that there is a scaling advantage. In this case, for the particular case of the parity architecture, the CD local driving also shows a slight scaling advantage compared to the baseline, but the rotated approach, just by modifying the schedule, is able to obtain a better advantage over the one of the CD. So I will just want to conclude. So I just, in the talk, I just mentioned that CD drivings are a possibility to use for schedule optimization, not only by adding terms, but by using this transformation and choosing them properly in such a way that we are obtaining only schedule modification. And the new schedules that we find perform better than the other one, and is slightly different than the usual quantum annealing, because I would say it's more within the size of the adiabatic quantum annealing. And as an outlook, there are various things we can see improve in this kind of approach, which are considering non-abelian transformation, which is part of the hypothesis we used in finding the derivation, considering noise in the approach, and reiterating the algorithm, which means essentially considering this considering this RA that we show at the end protocol as an initial protocol to apply the method again and get a further improvement. So that would be all.
Good.
Thank you for your attention.
Okay, so are there any questions for Glen? Anna.
Thank you for the very nice talk. So do you have an idea of how much, considering non-abelian transformations, would impact the computational cost of the optimization process? I guess it's
yes, that's a really good question, right? Because I didn't mention it, but for all the problems I studied, the computational cost, one has to do some work analytically, but then the computational cost is it's okay after some work analytically. But if you consider a non-abelian transformation, first of all, the work you have to do analytically before making it something which makes sense to try to compute is it's hard. Okay. So what we are trying to do at the moment is just, first of all, try to see how it would work if on a small system just by doing it, assuming that we don't care about the computational cost of computing, and then we want to see if how many terms you have to include to get a good improvement. If this is encouraging and we see good results, then we would put some effort in the analytics which is required. So it's the hypothesis of non-abelianity allowed us to essentially disentangle the times within the optimization processes, so we can optimize one slice, 1 point at a time. And optimizing 1 point is a very easy task because we have its previous point. So this can be done also with just a few points in the middle. It still works, and it's actually in line with the kind of way machines like D-Wave modify their schedule, is they put some points in the middle and allow you to modify the points. So this works pretty well. But doing this requires this hypothesis, and without this, we have no idea on how to simplify. The full approach can be done by, I think, not up to. It's more or less as what the usual problem of the exponential Hilbert space will kill you in the end if you try. Unless we find some smart analytical way to do it.
All right. Thanks.
Thank you.
Hi, thank you also from my side. In the very beginning, you said something about that you applied the scheme to to a binary perceptron.
Not this one, but the other scheme that I know.
Yeah.
Yes.
In my head, it's not quite clear how you. Can you elaborate on that a little bit, please?
Yes, sure.
Thank you.
So, first of all, sorry, this is. So first of all, how does this work? Let me just reiterate how this works pretty quickly. So we digitalize the problem. So now the problem has some finite points. You could find things about a stair instead of a continuous function, and now you have to try to use these stairs and find the best stair that you can solve the problem. And in this case, then we find that you can find the best stairs by increasing the points bit by bit. So in the case of the perceptron in particular, first of all, I have to mention, I was now going pretty quickly here, so there are we have some also other words on the topic. And in the case of the perceptron, we don't care about embedding. So that's a very hot topic now, and we just take the perceptron as a model as it is, and we simulate it. That's possible for when you're doing simulation, or if you're not doing some fancy simulation, but some full Hilbert space simulation, you don't really care about how hard is the model. That's something for the hardware implementation. So yeah, so first of all, when I talk about binary perceptron, I mean something that we are simulating, but I'm not talking about results that are embedded and then what you'd get if you put it on a device. I don't know what's related to this. So what we do is we take we apply to the training phase of the perceptron. So the binary perceptron, it's basically the most simple neural network you can use, and you can use it to classify some maybe not the most simple, one of the most simple. You can use it to classify some bit strings. That's one of the application of it, and that's the case we consider. And we consider the problem of training it. So the training can be seen as a minimization problem, and we tackle this problem with the algorithm. But the minimization problem is a very hard problem. Okay, so for example, simulated annealing gets stuck when this is done, right? So in this kind of problem, and the problem was studied also already previously by Zekina, who is with us in this work with quantum annealing, and quantum annealing was performing quite well. So we find that this approach performs quite good also on the perceptron, okay, when still not embedding. So if you embed, I cannot say what's going to happen if you embed. And so the only problem that you would have is that when you apply to this kind of problem which are more complicated, you need a second step because you get sometimes stuck in local minima. So once you get stuck in local minima, you essentially, the local minima is a bit rough, it's not smooth. You smoothen out your function and then you optimize again starting from the smoothen function. And this allows us to escape from the local minima in the different problems we tried, not only the perceptron.
Okay, thank you.
If you have a question, pass the mic back. You're very kind. Thank you.
Move this back. So I'm squinting a bit under the lighting, but when you were showing improvements to the scaling, so do we know where you actually get a qualitative change in the scaling rather than just a prefactor? Were you adding sigma y's to that? So in other words, we've got a Hamiltonian that's universal for quantum computing now, not just a transverse Ising. This also applies a bit to what Adolfo was showing, where you end up adding the term you would need to lift the transverse Ising to universal quantum. Does that change the scaling? Is that correlated? Do we know, or is that just happens to be the case?
No. So eventually, what we know is that if we add enough terms, it's gonna get to 1. So the scaling is gonna change completely, because if we lift the restriction on number of terms, the fidelity is gonna be 1, because the approach works perfectly. Just it's gonna be very hard to compute these objects. So there is some trade-off between the hardness of computing these objects and how well I can improve how well they perform. So the more effort I put in computing them, and the more I allow space to add new terms, the more the fidelity will improve. Regarding the issue of what happens, I would say I cannot say it a priori. What I can say is that I would imagine, so probably, I don't know if Adolfo is still online, maybe he has some insight on this. I would imagine, I think it's reasonable to imagine that maybe if the system is local itself, the more the system is local in its interaction, the more the local operations, the local changes, additions are going to be sufficient. So for the Ising chain, which is local in space, we find that this local approach is sufficient. But for the other approach, which we have totally lost the idea of locality, then the local driving, it's pretty weak and gives a weak improvement. But this is, but I cannot say, I cannot.
Is there a typo here? These terms look very similar. I'm wondering whether that's a typo.
There is an X.
YX and YD.
Yes. So this is a Z here. It's very light.
But this term is the same as this one, is I guess my point.
Yes, that's the J and the K should be inverted.
J and K should be flipped.
The
Okay,
J and the K
fine,
should be
understood,
flipped.
understood.
Oh, you have a very good eye.
Do you mean to index every alpha with a J as well?
Well, what? Sorry.
Sorry.
Thank you. Did you mean to index every alpha with a J? Like, do you have n variational parameters or something here, or?
I have what? N variational parameters?
Or how do you?
So
Do you mean to have?
variational parameters in this first term? Is that
In the first term, yes.
Okay.
Yes.
Okay. Then, so let's just take the one local. Can I just choose the alpha that takes me to the right state?
So the issue being that if you do it, if you do it fully, in the exact case, you would have the Hamiltonian with all possible terms, all possible imaginary terms, because the Hamiltonian is real, and essentially this is a way to truncate this sum. So now if I put all the terms, I'll get fidelity 1. Wherever the more I truncate, the lower I get my fidelity. But then the problem is that even if I've truncated to some terms, I don't know the coefficients. So this is a way to get the coefficients. But I cannot with just the first term solve my problem, because the other terms are within the exact solution.
Okay, maybe. So how many variational parameters do you have? All these.
Yeah, that's a good question. So this is the local CD. This is the CD approach, right? So not the one I showed before, not the rotated answers, right? So not the one I was discussing after. In this one, when you do it like this, you have a lot, right? So here I have, I'm using n squared parameters for this approach and n parameters for the one local. In the other approach, I'm using one variational, two or three, depending on, because I'm using them one for each schedule.
Okay.
So I'm using one per schedule, because I'm changing already the schedule. Here I'm adding many terms which have different coefficients, while in the other case I'm adding terms, I'm changing just the schedule, the 2 or 3 terms which are identifying the schedules depending on the architecture I consider.
Sure, but like if I was now just to ignore, say, HT, and I was just to use that A1 local, I could always just drive to, if I choose my alphas, right, just to take me from just local rotations from plus to.
Yes, you can drive. Just that in this approach, in the Contrabatic approach, we are making a requirement which is slightly stronger than maybe. Hopefully, I wrote it here. Sorry. Okay, I didn't even need to go there. It seems I just like that cartoon. So exactly. So we are making this assumption here. No.
I'll change the battery later.
Okay. So I think can you see the mouse?
Yes.
So we are making this assumption here. Usually, before you're trying to prepare your state, starting from the state in the ground state, and then you want to end up in the ground, and then you can do some rotation, as you said, and get there. However, here to be able to optimize, because we want a way to find the protocol before running the device, we make a requirement, and this is the requirement for contrabatic driving, is that the system stays instantaneously within the eigenstate. So if I do this rotation that you say, it's not going to stay during the rotation within the eigenstate. So that's not an allowed valid contrabatic driving, so it's not something we can be found within this framework. But it's a valid protocol to generate it. However, I would find it hard for you to give the good angles before trying it on the device in a many-body system.
Thank you.
Okay, we should probably conclude there. So let's thank Glen again for a very interesting talk. Thank you.